Could the singularity inside a black hole, with its potentially infinite curvature, literally rip the fabric of spacetime apart? According to Einstein's general relativity, all the black hole's mass is crushed into zero volume, resulting in infinite density and infinite spacetime curvature. That concept of infinite curvature sounds incredibly violent. It naturally leads to the question, could this extreme warping actually tear or rip apart the very fabric of spacetime itself? First, let's consider what general relativity actually tells us. It describes spacetime as a generally smooth, continuous fabric, a manifold in mathematical terms, that can be bent and warped by mass and energy. When the theory predicts infinite curvature at the singularity, it's essentially saying the warping becomes infinitely intense. Tidal forces, the stretching and squeezing caused by gravity, become infinite. The equations themselves break down. They can no longer describe the geometry or predict what happens next. Does general relativity explicitly describe a ripping process? Not exactly. It describes a point of mathematical breakdown, a pathology where the smooth fabric concept fails. It essentially throws up its hands and says, my rules no longer apply here. Now, almost all physicists believe that these infinities predicted by classical general relativity are not physically real. They are signposts telling us that we need a deeper theory, one that incorporates quantum mechanics to understand these extreme conditions. So what might quantum gravity say happens at the center? This is where we enter the realm of active research and theoretical speculation. Perhaps spacetime itself resists being curved beyond a certain enormous but finite limit related to the Planck scale, the tiniest possible scale in physics. The singularity would be replaced by a region of this maximum curvature. Quantum foam at the Planck scale, spacetime might not be smooth at all, but a chaotic, fluctuating quantum foam of tiny virtual wormholes and changing topologies. The singularity might dissolve into this fundamental fuzziness, transforming into something not describable by geometry at all, perhaps governed by more fundamental quantum information principles. Could any of these quantum gravity scenarios be interpreted as spacetime ripping? In a sense, perhaps. If spacetime ceases to be a smooth, continuous fabric and instead becomes a chaotic foam, or undergoes a phase transition into something non-geometric, you could colloquially describe that as a fundamental break or change in its structure, maybe even a rip from its classical form. Some theories might even allow for changes in topology, like the creation of tiny wormhole connections, which could be seen as a form of tearing and reconnecting. However, this wouldn't be the uncontrolled, infinite tearing implied by the classical singularity. It would be a process governed by the new, finite rules of quantum gravity. It wouldn't be a breakdown of physics, but rather the point where the ultimate laws of physics take over from the approximation provided by general relativity. So, to summarize, while general relativity predicts infinite curvature at a singularity, signaling its own breakdown, it doesn't explicitly describe a ripping of spacetime. Quantum gravity is expected to resolve this singularity, replacing it with a state governed by new physics. Some of these potential quantum states might involve processes that could be loosely described as a fundamental change, or rip, in the smooth structure of spacetime as we know it, perhaps dissolving into quantum foam or changing phase. But this would be a quantum phenomenon, not the infinite catastrophe of the classical picture. The fabric might transform, but likely according to deeper, quantum rules. Now, we've talked about the singularity as this point of breakdown within a black hole, but you might have also heard about a theoretical connection between black holes and wormholes, those hypothetical tunnels through spacetime. How are they linked, and does the wormhole emerge from the singularity? The connection comes purely from the mathematics of general relativity, specifically from the idealized solution describing an eternal, unchanging black hole, something quite different from realistic black holes formed by collapsing stars. This mathematical solution, called the maximally extended Schwarzschild spacetime, actually describes more than just a single black hole. It describes two separate exterior regions connected by a throat, which acts like a wormhole, often called an Einstein-Rosen bridge. Crucially, this bridge connects the event horizon of the black hole in one region to the event horizon of its time-reversed counterpart, a white hole, in the other region. So, in this specific mathematical picture, the wormhole throat is associated with the horizons, not the singularity. Furthermore, this Einstein-Rosen bridge is non-traversable. The throat pinches off so quickly that nothing, not even light, could actually pass through from one side to the other. And if you tried to enter the black hole hoping to reach the wormhole, you would inevitably hit the future singularity inside the black hole long before you could ever cross the bridge. The idea of traversable wormholes, ones you could potentially travel through, is a different concept requiring vast amounts of hypothetical exotic matter, with negative energy density to prop the throat open. These aren't predicted to form naturally from black holes. So while there's a fascinating mathematical link in idealized scenarios connecting black hole and white hole horizons via a non-traversable wormhole, it doesn't involve the singularity as a gateway, and it's highly unlikely to be relevant for the real black holes that form in our universe. Let me know your thoughts in the comments below. Thanks for watching, and see you in the next one.